Good evening, everyone. Welcome to the fourth workshop of Brainstorm 2026, Sri Lanka's premier healthcare innovation competition organized by the IEEE Engineering and Medicine and Biology Society at University of Moratuwa. Today, we are diving into an exciting topic with our theme From Pulse to Packet. This session is designed to give you insights into building end-to-end biosignal acquisition systems and understanding how physiological signals are captured, processed, and transformed into meaningful healthcare data. I'm sure this will be a valuable opportunity for all of you to explore the engineering behind modern healthcare technologies. We invite you all to stay with us until the end. Every healthcare monitoring system begins with a signal, but transforming that signal into reliable and meaningful healthcare information requires expertise in sensing, signal processing, and system integration. To guide us through this journey, we are delighted to have Mr. Avishka Herath with us today. He is a biomedical engineering graduate from the University of Moratuwa with experience in biomedical instrumentation, biosignal acquisition systems, and healthcare technology development. Mr. Avishka has also contributed to research focused on real-time ECG and PCG acquisition systems for healthcare applications. We are excited to learn from his insights and experiences in building end-to-end biosignal acquisition systems. So, without further delay, please join me in welcoming Mr. Avishka Herath. Over to you, Mr. Avishka.
Thank you, Isiri. I hope I'm audible.
Yes, you're audible.
Okay, thank you. Let me share my screen first. Right. All right. I hope you can see my screen also. So, yeah, today my presentation will be mostly based on building end-to-end biological acquisition systems. So, we know like we need to capture biosignals using as continuous analog signals, and then we need to do processing and we need to transmit them to acquire meaningful information out of that. So this will be the base of the presentation today. So before starting the presentation, I will just give a small introduction to myself. So my name is Avishka Herath, and I'm currently a junior lecturer at the Department of Electronics and Telecommunication Engineering at the University of Moratuwa. I obtained my bachelor's degree from the same university as well. I was a former research affiliate at the University of Sydney. And if you want to contact me, you can reach out to me through my LinkedIn. Right. So before starting any thing regarding building systems, we look at how and what are biosignals. So biosignals are actually, by definition, the physiological signals which are emitted and measured and monitored using biological beings. That means any signal which are emitted using a human being is called a biosignal. And based on the origin of these biosignals, we can classify them into several types. So in here, I have added 8 main types of classifications based on origin. And the first one is the electrical origin, the magnetic origin, mechanical, optical, acoustic, chemical, thermal, and impedance variations, which we can obtain in our body and measure that using different measuring techniques. So if we go into some details about these types of biosignals, the first one is the bioelectric signals. And this is the most popular type of signals that we have come across in biomedical acquisition. That is, for example, the ECG or the EKG, which is known as the electrocardiogram, or the EEG, which are also the brain signals, the electroencephalogram. And additional to this, there are EMG, the electromyogram, and also the EOG, which measures the electrical activity due to the eye movement. So most of the signals that we have seen in biosignals are electric signals, but it's not limited to only electric signals. So there are several other types of signals as well. For example, there are signals called biomagnetic signals. The biomagnetic signals are the examples of that would be the magnetocardiogram, which measures the magnetic field variations of the heart due to the electrical activity of the heart. So these are actually uh, very tiny, extremely weak magnetic fields. So it's not that much popular in measuring, but that is also another perspective that people use to see the electrical activity of the heart. So similarly, we have the magnetoencephalogram also. And another type of signal is the biomechanical signals, which occurs due to mechanical variations of the human. For example, the blood pressure, the arteries moving due to blood pressure, and also the chest movement due to breathing, and also muscle displacements when we are walking or doing some activity which are related to skeletal muscles. And another type of signal is the biooptical signals. So these signals actually changes the characteristics of light. So such as due to some variations of the characteristics, sometimes the light absorption rate uh, or similar other characteristics will be changed, and therefore for that reason we can actually measure these using some optical measurement techniques. So for some examples of that would be the EPG signal, which represents the blood volume changes of our body. The name of the PPG means photoplethysmography. And similarly, the NIRS signal or the near-infrared spectroscopy signal is also present to measure using optical techniques. Some other signals called as bioacoustic signals measure the sounds which are emitted from our body. For example, mainly the acoustic signals involved in our metabolism is the phonocardiogram, that is the mechanical activity of the heart. That means we can hear our lub-dub sounds, which occurs due to opening and closing and valves in the heart. And also another acoustic signal produced by our body is the lung and the airway sounds. So based on that also, there are several classifications which doctors could use uh, to monitor a patient. And another type is the biochemical signals. So these are not directly measured, but with recent developments, people have implemented these types of uh, chemical signal measurements into wearable devices. So new devices are able to measure these blood glucose levels or the pH levels of the sweat or the body, and also the amount of or the percentage of gases dissolved in our blood. So these are mostly chemical related signals which are generated from the body. And another signal is the biothermal signals, which is directly as the name it gives. So this is basically measuring our temperature of the body, which is mainly the surface temperature measured using thermography, or the core body temperature or the internal temperature of the body. And another type of signal is the bioimpedance signals. So in these signals, they usually measure the impedance variations. That means uh, these signals uh, due to these activities, the feature that changes in the body is the conductivity of the that particular uh, area. So, for example, in the galvanic skin response, what we measure is the conductivity of the skin, and that changes due to sweat and other factors as well. So, due to these, there are variations in these impedances, and what we do is we stimulate our body using an electric pulse, and we measure the voltage and get the impedance of that. So, similarly, there's another one called the electrodermal activity or the EDA signal. So there are 8 main types of signals that we classify as biosignals, which are emitting from our body. And this is the main workflow which involves the acquisition of the biosignal. So we start from our body, and from the body, there is the interface between our measuring hardware and the human being. So that is called the hardware-body interface. And after that, that change or variations are converted into electrical signals and transferred and processed using other techniques. So the first block which reaches is the analog front end, which actually conditions the signal as needed to be digitally converted. So then after the analog front end, it moves on to the analog to digital converter. So from this state onwards, the analog signals which we obtain from our body is converted into a digital waveform. And from there onwards, we can use digital techniques such as microcontrollers or computers to process these signals, and then we can transmit to remote locations that we can use this data for. Right. So this is the main acquisition flow of our uh, biosignal acquisition systems. Right. So now, as we discussed previously, there are uh, 8 main types of biosignals, and only one is an electric signal, and the rest are non-electric biosignals. Right. So we know that uh, for processing, we need some sort of electronic variations or some sort of electrical variations to uh, process using an electronic circuit. Right. So therefore, when measuring these non-electric biosignals, we need to find somehow a method to convert it into electrical variations. Right? Yeah. So as I mentioned, now these non-electric biosignals cannot be processed using any electronic circuits. Right? So therefore, we need a method to convert them. So for that, people have developed electrical transducers to convert this non-electric energy into electrical energy. Right? So the term transducers means it converts one form of energy into another, and since this is an electrical transducer, it will convert this into electrical signals. Yeah. And yeah, these are some examples of hardware-body interfaces of these non-electric biosignals. So the first one would be an optical interface, which measures the PPG and the SpO2. In here, the SpO2 means the blood saturation level. And in this, this just shows some images of how these optical interfaces are used to measure the PPG. So as I mentioned before, what it does is actually due to the physiological changes, the the light absorption rate or any other light characteristics change. So therefore, by means of sending a light signal and measuring the reflected or absorbed light signal, we can get an idea of how that physiological parameter changes. Right? So, for example, in here, what we do is uh, we are using a red light and an infrared light to transmit through our finger, and we have a sensor on the other side. Right. So, what happens is when there is oxygenated blood in this fingertip, what happens is this infrared light is absorbed into this oxygenated blood, but it does not absorb red light as much as the infrared light. So therefore, when we measure using the sensor, we will see a ratio such that the concentration of the red light is higher than the infrared light. So similarly, in the deoxygenated blood, the vice versa would occur. That means when there is deoxygenated blood, it will absorb red light more than infrared light, and therefore this infrared light would pass through the sensor, and we will now see um, a higher intensity for the IR beam, but not for the red beam. So therefore, if we like continuously monitor these sensor signals, that means the variations of this red light and also the infrared light, if we monitor these continuously, we will obtain a waveform using these ratios, right? So based on that waveform, if we plot that, that waveform is actually called the PPG signal. And using that waveform, we can derive some values using some modules people have developed. And from those modules, we can actually get the SpO2 value or the blood oxygen saturation level using that waveform. Yeah, so this bottom image is also a similar representation where it shows the low absorption and high absorption within the blood. So when there's low absorption, more light is transmitted towards the sensor. And when there is high absorption, only small amount of light intensity is transmitted towards the sensor. Yeah, so that's an example of the optical interfaces which we use to measure PPG and SpO2 variations. And this is an example of how the magnetocardiogram is obtained. So in here, we place a magnetic transducer on top of our skin. So what happens is due to these electrical pulses, we know that there will be magnetic field changes that occur. So therefore, whenever there is a magnetic field change, this this transducer could detect that, and it can convert it into a voltage waveform, and then use that signal for further processing. So one advantage of this MCG is that since these are magnetic signals, the magnetic fields are not absorbed, or it's not uh, attenuated when passing through our skin from the starting from the heart. So therefore, there's very low attenuation compared to the electrical signals. So therefore, this is a method of a non-invasive measurement of the activity of the heart. But the downside of this is this magnetic field variations are very, very weak, and therefore usually they are in the nanotesla range or picotesla range. So therefore, it's not a like due to the other magnetic fields that are happening in the environment, it is very hard to distinguish between them and the signal because the signal is very small. Yeah, so this is also a continuously developing field which people are researching currently. Yeah, so that's about magnetic interfaces. And another type of interface is the mechanical interfaces, which we use to measure biomechanical signals, such as movements of the skeletal muscles and movements of hands and chest movements and similar things to that. So in here, the transducer which we use is actually called a resistive transducer. So this resistive transducer is called the strain gauge. So what happens is when there are any compressions or tensions, this due to the length and the width variations in these conductors, there will be a resistance change. So what we do is we measure this resistance change using a circuit called the Wheatstone bridge. And I think you may have already know what a Wheatstone bridge is. So using a circuit called Wheatstone bridge, and we can measure this voltage signal using this strain gauge. If we fix this strain gauge into a muscle that we like to measure the movement. Yeah, so these are some examples of some hardware body interfaces which are for non-electrical signals. Yeah, so if you might notice in each of these ones, what we do is we usually get some sort of signal which interact with the our physiological variations, and we have another some sort of device which converts that variation into a electrical voltage variation or a current variation. Yeah, so that's what we are going to do. And in measuring electrical biosignals, we do not need such transducers or such uh, some different sort of components to gather them. So what we are doing is when measuring these electrical biosignals, we are using some biopotential electrodes, and we are directly capturing those biosignals using that. So in here, actually, even though we say we do not use any transducers, this biopotential electrode is actually a passive transducer. So we don't need to give any power to that, but it acts as a passive transducer. So I'll say how. So what happens is we know that uh, our charge carrier in our body is ions. We don't have electrons, right? So, and in wires and in electronics, it's mostly electrons that carry the current. So what happens is these uh, biopotential electrodes are able to convert these ions, the variations in these ions, into variations of these electrons. So therefore, uh, when there are variations in the electrons, there will be variations in the potential difference and also current, thereby generating a voltage. So this is also a kind of a transduction, and this transduction is carried out using an electrochemical reaction, which is occurring on the uh, interface between the electrode and our body. So, for example, if we use a silver chloride electrode, we do have this reactions occurring on the surface, which is the reduction reaction to convert it into silver, and also the oxidation reaction to convert it into silver chloride. Right. So this image shows the how these interfaces are formed. So this bottom gray color area is the electrode, and this is the light blue color area is our skin, or sometimes it may be the gel that we are using for electrodes. So between these electrodes and our body, now there will be some charge attractions happening. So therefore, when this redox reaction is happening, it will attract charges, and therefore when it attracts charges, it will form a layer of charges in here. And when that layer is formed, it will attract other types of charges as well. So which means when a positive layer is formed in here, so now there's a positive uh, electric field appearing in here. So therefore it will attract negative ions towards it. So therefore now we have a charge separation in this, and this charge separation is called the double layer of this electrode electrolyte interface. So therefore, due to this charge separation, there will be something called the half cell potential generated across this electrode. Yeah, so this process is actually what converts these ions into electrons. What converts these ion variations into electron variations. Yeah, so actually people have developed these methods, and they have researched on these behaviors, and they have found equations to calculate this half cell potential. And we have an equation called the Nernst equation to calculate this half cell potential. And yeah, using this, we can actually calculate this value based on the concentration of our electrodes and electrolytes. So yeah, so these are actually not ideal behaviors. These are actually practical or sort of non-ideal behaviors which are happening in these electrode-electrolyte interfaces. So therefore, people have sort of developed circuit models to represent these non-ideal behaviors using circuit elements. So we'll have a look at that as well. And if we like take that electrode-electrolyte interface, now we can represent that same interface using a circuit model. So that means we have electronic components in that model. So this is the equivalent electrical diagram of this, and this cell in here is actually represented by the half cell potential. So we can actually calculate our um, half cell potential using our concentrations and other constants in here, and then we can substitute this uh, into this cell, right? And these other this parallel resistor capacitor is actually representing the impedance across this double layer. So that means if you can go to the other slide. So what happens is, now due to this interface in here, what happens is we have half cell potential, which is represented by this cell, and also in addition to that half cell potential, there is a barrier to um, charge conduction, right? Due to these charges in here. So that barrier is also kind of can be represented by using a resistor and a capacitor. And based on research people have developed, we can just simply represent that using a parallel resistor and a capacitor. And this other resistor in here is actually representing the electrolyte resistance, which means the resistance which occurs due to this when an electron is traveling through this fluidic area, and that resistance is called the electrolyte resistance. Yeah, so this is basically what people have developed for to represent this electrode electrolyte circuit model. Right now, the thing we discussed is actually the circuit model or the interface for the electrode and the electrolyte. But somehow now they need to touch our skin also, these biopotential electrodes. So therefore, due to the non-idealities in the skin, there will be additional components which are added to our circuit model. So in here, so in the left diagram in here, we can see there's an electrode in here and this gel is in here. So this gel is the electrolyte that we talked in the previous slide. So therefore, based on the information on the previous slide, what we can do is we can actually represent this electrode and the gel using this circuit combination, which is representing the half cell potential, the parallel, the resistance, and the series impedances, and also this series resistance for the electrolyte. But from there onwards, what happens is we have our skin also, the outer layer, which is the epidermis, and the dermis and subcutaneous layers are there. So therefore, similar sort of circuits can be used for that as well. So in here, if you can see this circuit is actually a repetition of the top circuit that we have. So because in here also there will be a double layer form, and we can actually model that area as using the same way. So yeah, so this is basically what the combination of the circuit looks like. So if we like include if we need more accurate results, or if we need to model this very accurately to get the correct variations, we can actually include this sweat glands and sweat ducts into this also. So uh, that's optional. But if we remove this and analyze our system, what happens is we will get slightly off results, which are actually coming in the practical scenario. Yeah, so now this is our equivalent circuit model for the whole skin and the electrode interface, right, which contains our double layer, the electrolyte interface, and also the skin skin variations, which represents several impedances in there. So now what happens is, since there are capacitances in here, now this is not a resistor anymore, right? So this is more of a impedance now. So therefore, when there's an impedance in there, what happens is this would have some sort of dependency on the frequency. Right? So due to that frequency dependency, what we will have found out was there is a impedance characteristics of the skin, and what we what they have found out was when the frequency of the signal which is passing through uh, this circuit increases, the impedance is decreasing continuously in this sort of trend. Uh, that is also very implied because we know that in high frequencies, these capacitors will get shorted and it will provide a low impedance path. So therefore, when it goes into higher frequencies, this would have a lower impedance. But what happens is in lower frequencies, we have a higher impedance in here. Yeah, so so based on that, what you can actually deduce is that if we like apply a very high frequency signal to our body, that means that signal would see a very low impedance pathway, right? So that means it can travel through our body rather than a DC signal. So therefore, we must be very careful when operating with frequency also. Yeah, so in here, like people have developed some rules of thumb for this electrical impedance, and the values are like this. The electrical impedance for skin per square centimeter is 200 kilo ohms for one when a 1 Hz signal is considered, and it's 200 ohms when a 1 megahertz signal is considered. Yeah, so this can be used as approximations when designing our circuit because modeling this whole one is not very practical in circuit design. So what you do is we can replace this uh, whole circuit or the whole network of circuits using this single impedance, assuming that we have some sort of frequency in our design. Yeah. So this is basically what the skin electrode interface looks like. Yeah, so now after the skin electrode interface, what happens is now the we have found a way to convert our electrical we have found a way to convert our physiological variations into electrical signals. So now after that, what we can do is we can capture them using a wire which is connected to the electrode or the transducer. We can capture them using a wire, and then we can actually further process them. Right? So these processing interfaces are called as analog front ends. So this actually involves several circuits in here, which is used to amplify signals and also filter out unwanted noises. So yeah, so the amplifier is the main component of the analog front end, and as we know, this ideal operation amplifier is actually characterized by these features. That means we have an infinite gain and we do not have an offset voltage. That means the difference between the input voltage is same. Also, we do have a high input impedance and the output impedance is zero. And also, this ideal op amp would support up to infinite amount of frequencies. That means it will give a infinite bandwidth. Yeah, so now this is how our op amp would look like if these ideal, all these ideal or ideal conditions would hold. This is how it would look like. But yeah, but in the practical case, this will be violated. So we need to make sure that we design in such a way that it is in a near ideal scenario. Yeah, and so based on these assumptions or the characteristics of the ideal op amp, we can derive three basic rules. So the rule number one is that the no current flows into either input terminals of the op amp. So that is actually basically given using the high infinite input impedance. And the rule number two is that when the op amp output is in its linear range, the two inputs are at the same voltage. So that is basically given using infinite gain and also no offset voltage, because we know that uh, in these amplifiers, there is some sort of output which is given, right? So if we have an assumption that our input terminals are at the same voltage, that means our input signal is zero. So that means we should have an infinite gain to for this rule to work. Yeah. And likewise, we have the rule 3, which is like in when using these amplifiers, we have to always give the feedback into the negative terminal. We can't have positive feedback in these systems. Right? So for this system to become stable, we have to give negative feedback. Yeah, so that is the main 3 rules that governs this design of amplifiers in these analog frontends. And once these rules are held, we can actually design a good analog front end to amplify our biosignal. And these are some examples of the amplifier circuits that are typically used in biosignal acquisition. The first one is the buffer, which is used to isolate between two stages. And some you might already know. And the next one is an inverting amplifier, so which amplifies with a gain and also inverts the signal as needed. So the third one is the non-inverting amplifier. So in the non-inverting amplifier, it is same as the inverting amplifier, but the only difference is it's not inverting the phase. Yeah. So the fourth one is actually the summing amplifier, and the summing amplifier would look something like this. So this is basically used to actually superimpose multiple signals on top of each other. So if we have several signals, we can add them together and get the output. Right? So that is which is basically the summing amplifier, and the gains of each of those signals can be determined using these resistor ratios that we have in these amplifiers. Okay, so the next one is actually the transimpedance amplifier. So this transimpedance amplifier, what it does is it converts an input current into an voltage. So one example that it would be useful is that when if we like use a photodiode as our sensor or as our transducer, what the photodiode does is it changes the conductivity or the current flow through that diode. So that means the variation is happening through a current. So, but in these electronics, we do not typically use current variations. We use with voltage variations. So therefore, we need some kind of way to convert this current variation into a voltage variation. So in those sort of scenarios, we can use a transimpedance amplifier to convert that photodiode signal variation into output voltage variation. Yeah, so that's one use case of a transimpedance amplifier. And the next one is the differential amplifier. So this is basically used to get the difference of a signal. So for example, this is mostly popular with the electrical biosignals. So in here what happens is, uh, for example, in ECG, we have to get the difference between two electrodes, which then forms the lead, so, which forms the lead in there. And when those difference between the electrodes are taken, what happens is we can get the actual variation and we can amplify that. So therefore, for those sort of reasons, we are using a differential amplifier. And in this differential amplifiers also, we can configure the gain by tuning these resistors. And typically, we make sure that this feedback resistor and this ground resistor are equal to make sure to both the input signals sees the same impedance. And also similarly, we can make this input resistors similar also. That is typically to maintain the symmetricity of this circuit. Yeah, so that's what a differential amplifier is. And an improved version of the differential amplifier is called the instrumentation amplifier. So in this instrumentation amplifier, in addition to this differential amplifier stage, if you can see in here, the last stage of this is a differential amplifier. And in addition to that, we have two buffers included in front of that. So basically what this does is we are using this instrumentation amplifiers to actually amplify very tiny signals, very time signals which are in noisy backgrounds. Because compared to the differential amplifier, this instrumentation amplifier has a better response to avoid noise. Right. So that is the main purpose of this instrumentation amplifier. And also, since there are two stages involved in this, there is a we can actually gain higher. We can actually like get higher gains in this instrumentation amplifier as well. Yeah. So that's basically what different types of amplifiers are, how they look like in which are used in typical analog front ends. Yeah. So that's about the amplifier circuits. And after amplification, what we do is we need to clean our signal. So whenever we acquire our signal and when we amplify the signal, we also amplify the noise as well. Right? So when we amplify the noise, what happens is we need to remove our noise from our signal. We need to separate them, and we need to transfer the signal only into the next stages. So that is what is called signal conditioning. Yeah, so in here, if you can see in the diagram, you can see where there's a very noisy biosignal in here, which is a noisy ECG. And after this goes through signal conditioning, it will convert into a noise-free ECG signal. Right? So that is the purpose of signal conditioning. Yeah, so signal conditioning refers to the process of manipulating a signal in such a way that it meets the requirements of the next stage for further processing or digitization. Yeah, so this is what actually signal conditioning is. So actually the amplification is also part of this signal conditioning. That means we can get a low amplitude signal and we can amplify that, or else we can get a high amplitude signal, or we can attenuate it. So this attenuation is basically what happens to noises, and this amplitude increase is basically what happens to the amplifiers. Sorry, the signals. Yeah. So when there's a noisy signal, it will output a noise-free signal after this signal conditioning. Yeah. So there are several other things as well. So the main things which we are focusing in this workshop would be the amplitude, the amplification, and the noise in the recorded waveforms. Yeah, so now, as I said, we need to apply suitable filters to extract the signal from these noisy recordings. So this application of the filters are actually based on the signal of interest. So for example, from this diagram, we can see that if we get an EOG signal, this EOG signal is only spread across 0.1 hertz to 10 hertz. But the EEG signal would spread across 0.1 hertz to 100 hertz. So similarly, there are several ranges for these signals. So we need to choose our filters based on the signal of interest. Yeah. So there are several types of filters that we can use for this. So there are actually four main types of analog filters. The first one is a low pass filter. That means if we want to cut off these high frequency noises from our signal, we need to apply a low pass filter to it. So that means the low frequency is passed to the next stage. And if you want to cut off these DC biases or these DC potentials from our signal, so that means if you want a signal that is varying about zero rather than some sort of DC signal, we can actually implement a high pass filter to that. So when this biosignal is passed through the high pass filter, the DC biases will be removed and all the signal will be passed. So the combination of that high pass and low pass filter is called the band pass filter. Yeah. So similarly, for simplicity, we can just apply a band pass filter to this signal of interest, and we can get the signal also. Yeah, so in addition to that, sometimes there are noises within the band of the signal. That means if you can see in here, so let's say this, I think this should be ECG, electrocardiogram. Yeah, this should be ECG. So in this ECG signal, this signal has a bandwidth of starting from 0.1 hertz up to 100 and 150, about 120 hertz. So this has a bandwidth of 0.1, 1 to 120 hertz. So, but one common issue with ECG is that we know the power line uh, noises is usually in the 50 hertz range. So therefore, now our power line noise is inside this signal bandwidth. So therefore, we need some sort of way to remove that 50 hertz noise from our signal of interest. So therefore, what we do is we apply a filter called the notch filter, or else we call it the band stop filter. So using the band stop filter, we can actually remove that 50 hertz noise um, from our signal. Yeah. So that is how basically how we decide what filters we need to use in signal conditioning to get remove the noises and get our signal. Yeah. So after we get our signal, that means after we amplify and after we remove the noises from our recordings, what we need to do is we need to convert this into a digital waveform. That is needed because we cannot do any further processing using analog signals. So we need to convert this into a digital waveform, and we can use it within a computer for to extract some meaningful information. Yeah. So therefore, for that stage, we are using the analog to digital converters. So what it does is basically continuous. It converts the continuous analog signals into discrete digital signals. Yeah, so in these ADCs, there are several key parameters that we are interested in. So the first one is the dynamic range of this ADC. That means um, this is the range of the amplitudes that we have in our signal. So for example, in this signal that you can see in here, this has a dynamic range of 1 millivolts in here, right? So based on our ADC, that could represent several levels in our digitized signal. Yeah, so the other parameter that we are interested in is the resolution of this ADC. That means it represents the minimum voltage value that can be shown in a digital signal. That is called the resolution. So, for example, if we take the waveform in here now, what we are doing is we are converting this sinusoidal waveform into a digital signals. So what we do is we are just sampling, or we are extracting the data um, from several points in this continuous waveform, right? So this red color arrows or the red color lines represent the points we are extracting our data from. So unlike in the analog waveform, we have all the data that we need, but in a digital waveform, we only have data at some particular interested points. We don't have a continuous uh, data for our waveform. So what happens is, even though we are like uh, sampling in the time domain in here, another factor involved in our digitization is that there are several levels that we can map those into. So for example, we are actually using a 3-bit ADC in here. So that means if you are using a 3-bit ADC, we have 2 to the power 3 bits of levels. That means 8 levels that we can represent our signal in the digital waveform. So what happens is whenever we extract uh, uh, a signal from this analog, uh, whenever we extract some data from this analog signal, this data would not always correspond to a certain level. So what happens is this will automatically shift to the closest level, and that would create an error in here. So similarly, um, all these points would have these errors because we can't actually map it straight away onto this particular point because we don't have enough resolution uh, in our um, ADC. So, for example, if we have let's say we have a 12-bit ADC. That means we have actually 2 to the power 12 a number of levels that we can represent our signal. So therefore, if we use that, we might be able to get an accurate representation of this digital waveform, which is closely similar to the analog waveform in here. Yeah, so that is basically what is the resolution. Yeah, and also the other key parameter that we are interested in is the sampling rate. And in sampling rate, we actually have an interval of signal measurements, right? So for example, in here we have for this 3-second signal, we have 25 samples in here, and this H you can see in here is the time between two different samples. And if we get the 1/over value of this time difference, we will be able to get the sampling rate of this. So that is what's called sampling rate, the rate at which we are extracting data from our analog signal. Yeah, so the only constraint in selecting this sampling rate is the Nyquist criterion. So this Nyquist criterion means we need a sampling rate of at least 2 times the highest frequency of our signal. So for example, if we have the ECG signal in here, so our highest frequency in the ECG signal is 120 Hertz. So that means for our ADC, analog to digital conversion, to accurately work, we need to have a sampling frequency of at least 240 Hertz. So if we increase the sampling frequency, it will be better, but it will also uh, have more data for us to handle now. So it will lead to high data in our storages. Therefore, there's a trade-off between how high we can increase our sampling rate also. So the minimum is actually limited by the Nyquist theorem. Yeah. So that is basically what we are interested in these ADCs. Yeah. So these are some examples that we can show here. So yeah, I need to say before that is that in these modern analog front-end ICs, they do not contain only the analog parts in that. So these AFP ICs, they usually have the ADCs built into it also. So therefore, with that, these ICs would have both the things together. So we can input our analog signal and we can get the digitized output to measure correct to process it into the next stages. Yeah, so this is an example of the ABS 1298 analog front end. So in here you can see there are several other things that we have. So there, if you can see, there's a sigma delta ADC in here. Uh, there is the SPI protocols in here embedded into it, which are digital protocols. And we have this programmable gain arrays in here, which is basically a instrumentation amplifier, which can change the gain in here. And there are some sort of internal filters as well. Yeah, so this is how an analog front-end IC would look like, which has inbuilt ADCs. Yeah, so this is mainly for uh, biopotential measurements which involve electrical signals. That means we can actually measure differential signals such as ECG, EEG, EOG, and EMG using this. But there are several other biosignals as well as we discussed before. So therefore, for those, we have several other analog front ends. So in here, this is an analog front end of a optical interface. So what we do is we have this IR and the LEDs in here. Right? So this IR and LED will be internal drivers that are used in these ICs, and based on that they will light these LEDs appropriately, and based on the reflection, it will be measured using the photodiode as we discussed, and this photodiode variation would be used for an ADC in here, and this ADC is then transferred into further processing stages. So this is how a optical interface would look like if you're measuring the VPG signal or the SPO2 signal. Right, and this is an example of the of a bioacoustic signal when we are measuring that. So in here, we actually have the mic and also the ADC inside this. So therefore, if you can see in here, there is this section is actually the mic, which captures the sound variations, and it will uh, transfer this into the amplification stage. So after this amplification stage, there is an ADC, and in here after the ADC, there is a digital signal processor, and also then it will transfer it into the further processing stages. Yeah. So this I wanted to just show how these commercial integrated circuits would have these analog front ends and the ADCs integrated into them. Okay. Right. So after this signal is digitized, then what we can do is we can actually use that for processing. So we do the processing using microcontrol units, and yeah. So when we acquire this digital data into the microcontroller, what we have is we acquire it through several protocols. So this is some examples of such protocols, and the first one is the I2C. So that we show in the previous slide, and in here the I2C has some has a two-wire configuration, which has a clock and a data path, and also it is able to use with multiple peripherals based on the addresses given to them. Right. And also the another protocol is actually the serial peripheral interface, or the SPI protocol. This would involve multiple wires in this, and the main advantage of this SPI protocol is that it has the ability to transmit and receive data at the same time, unlike in the I2C protocol. Yeah, so therefore, this is also actually very fast compared to the I2C interface. Yeah, so therefore, this will have some protocols which are used in these modern ICs. Yeah, so the other one is the I2S interface, which is mainly used for sound acquisition. So, for example, if our transducer is capturing sounds or bioacoustic signals, we need some sort of device uh, which like uses I2S protocol to communicate with the microcontroller. Yeah, so those are various protocols which you can use. And after we obtain those data um, into our microcontroller unit, we can use several techniques to use this in real-time systems. So one technique is actually called the direct memory access technique, which is abbreviated as the DMA. So in this DMA technique, we have the ability to like get these data into our registers, which is inside the microcontrollers, without making the use of a CPU. So we just can the CPU can work on another thing, and in the meantime we can directly store this data into the memory. So that is called the direct memory access feature. Yeah, so therefore that is one technique that we can use for real-time systems, and another other types of techniques which are used for data buffering is called the single buffering technique, the double buffering technique, or else it is called also as the ping-pong buffering, and also the circular buffering techniques. So this is mainly used to manage the flow of data while in the microcontroller. So for example, in the double buffering techniques, what we do is we get the data and we store it in our registers, and we divide the data storage into two parts, and we process them independently one by one. So therefore, there will be no overlap, or there will be no data replacing happen, because we are using two independent sections to store and process data. Yeah, so that is some techniques that you can use in the microcontroller for these when implementing these real-time biosignal systems. Yeah. And after this, yeah, and this is a comparison between these microcontrollers that we can use for these systems. And I have provided three comparisons, which is the Arduino and the ESP and the STM32 F4 series MCUs. And out of these, the simplest one is the Arduino, and it is a beginner friendly uh, uh, my microcontroller or a development board. So that's the only advantage in that, and there are several disadvantages in that, because if you can see this ADC row in here, this has the lowest resolution in our ADC, and also it has very low IO pins that we can use in this, and also it also has a very low frequency that we can use. So therefore, the only advantage is that it's beginner friendly and it has low power consumption in this, but the rest it's not good good for implementing good real-time systems. So the next two microcontrollers are the ESP32 and the STM32 series development boards. And in that, these both of these are very advanced microcontroller development boards. The main advantage of this Nucleo board or this STM32 boards is that it has a higher number of pins. So therefore, there is the ability to connect more number of peripherals into them. And also, it has a very low power consumption in this. But the one downside is that it is a very advanced uh, development board to practice, because it is using the STM32 cube ID based uh, programming, and it will have a steeper learning curve compared to the others. Yeah, yeah. So in comparison, the main advantage of this ESP32 microcontroller is that it has built-in Wi-Fi and Bluetooth. So therefore, we do not need an additional peripheral to transmit data after processing um, within the microcontroller. But due to that reason, the main disadvantage is that it has a very high power consumption in this. Yeah. Yeah. So this is the overall comparison of these MCUs that you can use to decide on which one to use based on the type of application that you are using it for. If you are building a very, if you want to build a very compact and a very advanced system, it's better to go with an STM32 microcontroller. And if you want to build a proof of concept or a very simple prototype or some sort of initial testing stage circuit, you can go on with a Arduino um, development board. Yeah, so that's basically the comparison of these microcontrollers. And after this, after we capture this data, and after we process this, we can use this to transmit into real-time systems. As I mentioned, there are too many types of protocols that are available and used in modern days. So that is the first one is the Bluetooth Low Energy protocol, and in that it's just used for wearable devices and also continuous streaming onto a local device like a smartphone. Um, and the other one is the Wi-Fi protocol. So this Wi-Fi based protocol is actually used for stationary devices. So they are not mainly used for the wearables. And in this Wi-Fi, it's better to directly push data into a cloud rather than communicating with a streaming to a local device. Yeah. So after this data is acquired using the microcontroller, what we do is we usually create packets of data as we need, and based on that, we can transmit these packets one by one or multiple at a time based on the capabilities of our wireless modules. Yeah. So for these wireless modules, there are several manufacturers that make these wireless modules. For example, the Adafruit, the Microchip, and the Nordic Semiconductors modules are available. Yeah, so that's basically about what we do with wireless transmission. And after this transmission is done, what we do is we can use this for further stages, such as we can use this for visualizing through interactive applications. So people can interact with that and measure any thing that they need. And also, more importantly, this transmitted data can be used to create data sets and also used to like create to train or to use in deep learning models to classify between different patients to identify it as healthy or not healthy in different types of scenarios. So that's the end goal of these biosignal acquisition systems to help the advancements of healthcare systems. Yeah, so I'll just continue my, sorry, I just end my presentation by explaining that by showing you an example project that is done on this topic. So this is a project that I have been working on, which is to build a simultaneous ECG PCG acquisition system. And in that, I developed a small device that was able to accurately capture both simultaneous or the acoustical signals of the heart activity, right? So therefore, we used a uh, stethoscope plus digital microphone based system to capture the heart sounds and the electrode based system to capture the electrical signals of the heart. So this is what our main controller board looks like, and in here you can see all the stages that we have discussed in here. So if you go through the flow, the ECG signal is inputted in here, and after it is inputted, there are several ESP protection circuits and filters involved. So I did not talk about this ESP protection circuits and in this workshop, and those ESP protection circuits are mainly used to protect the user from or protect the devices from very high voltages which are which are building up on the patients or the human beings. So therefore, for that, we have ESD protection, and also additionally, there are several patient protection resistors also in this to protect the patient from stimulating signals produced using this our circuit. And these filters are used to stop uh, several artifacts which are involved in ECG acquisition. And after that, this is directly sent to an analog front end. And this analog front end, we can, after this converts into a digital signal and it will send to a microcontroller unit to further process the signal. So after this microcontroller unit, it will send it to the Bluetooth module, so which is on the downside of the bottom side of this same board. So it will send to this BLE module and it will transmit the data into a remote computer to further process it. Yeah, so that's basically what's happening in this, and this is how the overall flow looks like. So this ECG, after placing this device on the human body, this AGAGC electrodes, which we discussed, would capture the electrical signal of the heart, and also this microphones would capture the ECG signal or the phonocardiogram, which is the bioacoustic signal of the heart, and it will be transmitted and converted and transmitted to remote computers for real-time noise cancellation and signal visualization, and finally for classification of patients. Yeah, so with that, I have come to the end of my presentation here, and yeah, so thank you everyone for listening. You can ask any questions if you have.
Thank you so much, Mr. Avishka, for that insightful and inspiring session. As Mr. Avishka mentioned, it's time for our Q&A session. If you have any questions, feel free to unmute and ask, or you can send your questions in the chat also.
Yeah, so there's one question. The question is, I'll read out loud. I'm currently working in a device to estimate blood pressure using a cuffless method, using PPG and mechanical compression of measurements in blood vessels. How can I choose the best sensors to measure the inputs? And what will be the hardest issue in my proposed system? Yeah, so you're using a cuffless method, using PPG and mechanical compression of the blood vessels. Yeah, so when choosing these sensors, actually you need to initially first find the specifications of your required signal. So for example, you might have uh, the frequencies of these PPG signals, and you might have some sensitivities of this. So you can find the relevant ICs which have the sensitivities of that you require for the PPG waveforms. And based on that, you can create a list of sensors, and you can choose the other. Uh, you can choose the single sensor which mostly match your conditions. Yeah. So, and for the mechanical compression of the blood vessels, if you're using a cuffless method, you might face problems in like placing these sensors in your body, because as there is no mechanical support to hold these sensors, if I understand this correctly, as there is no mechanical support to hold these sensors, you might face issues when placing these sensors in a wearable kind of device. Yeah. I hope I answered your question, and if I did not, you can ask any follow-up. Can the multimodal sensing improve significantly the accuracy? Yes, it can. If you're asking uh, about the project I explained just now. So if you're asking about this ECG PCG acquisition system, uh, the, the multimodal sensing could improve the accuracy, because, for example, what we are actually seeing is we are weaving the cardiac activity in terms of two different perspectives. So in the ECG signals, we are weaving this cardiac activity through the electrical signal, and in the acoustic activity, we are weaving this uh, cardiac activity through the mechanical signal. So therefore, those two signals should have a correlation in between them, because that's the mechanical activity is just a response to the electrical activity. So therefore, based on how the delays work and how those signals are correlated, we can actually find different types of defects involved with the valves of the heart. Yeah. So yeah, that significantly improves the accuracies. So this is the same for the other multimodal sensings as well. The purpose of multimodal sensing is to weave the same organ using two different perspectives to gather more information. Right. So there's another question in here. Is it if it possible when we use a wearable band in the wrist? Yeah. So okay. So measuring the PPG signal is not actually very easy, because the placement is actually a major concern in measuring these signals, because if you are not directly positioned into the arteries to measure the blood oxygen levels such that it interacts with the blood oxygen levels, our signal would be very small, or it will not there, it will not be there at all. Yeah, so therefore uh, you might need to think about the positioning of the sensors as well, so that you can use that repetitively. Can any interference happen to ECG signals when using ESP32 from Wi-Fi? Not really, not. The ECG signal bandwidth is usually from 0.05 hertz to 150 hertz. You consider the maximum range. So the Wi-Fi is operating in 2.4 gigahertz. So therefore, there is no direct relationship with that frequency. So the only concern is that it will have more power dissipation, and also the 50 hertz noise would come into play. Yeah, that's basically it. All right, so there's another question in here. And another product we are developing is a muscle stimulation device. What are medical grade conditions we want to consider when giving electrical pulses to the body? Yeah, so there are, okay. Actually, if you want to like find out all the medical grade conditions, you might need to refer to some sort of documents such as from the FDA released standards, or else the IEC standards, which are directly related to this medical instrumentation related signals. So they have specified the maximum amount of currents for that particular frequencies, which can be given to the human body. So you need to make sure that those are not passed. Okay, you're welcome.
Thank you everyone for your insightful questions. That will be the end of our Q&A session. So thank you once again, Mr. Avishka Herath, for the valuable and insightful session. We learned a great deal about biosignal acquisition systems and how physiological data is transformed into meaningful healthcare insights. And your explanations and the real world perspectives gave us much clearer understanding of the engineering behind modern healthcare technologies. We truly appreciate your time and for sharing your knowledge with us today. Thank you. And thank you everyone for joining us this evening. We hope you enjoyed the session and gained valuable insights from it. Have a great day ahead and see you at the next Brainstorm 2026 session. Thank you.